Introduce our speaker, Dr. Sumit K. Chattopadhyay. Dr. Sumit K. Chattopadhyay received PhD in Electrical Engineering from IIT Kharagpur in 2016. After having his BE degree in Electrical Engineering from Budwan University, Budwan, India in 2004, and MTech in Industrial Electrical Systems from National Institute of Technology, Durgapur in 2006. He joined Laser and Turbo Limited, Navy Mumbai, India, where he was responsible for power electronic system design of multiple industries and mission critical naval projects executed for the first time in India. He worked in L&T until January 2010. From January 2010 to March 2015, he was a full-time research scholar with Department of Electrical Engineering, IIT Kharagpur. From March 2015 to 2016, he has served as a scientist of HVDC grid system R&D with ABB Global Industries Service Limited in India. In 2016, he joined back to IIT Kharagpur as the first postdoctoral fellowship of Electrical Engineering Department to explore further the use of level double network in various applications. He has nearly 5 years of industrial experience working in the area of power electric converters for renewable energy, naval defense, and HVDC. He has proposed a new series of multi-level inverter topology using level doubling network. He has filed several patents and published papers on this topic. His area of interest are power electronic converter topology, modulation, and control for renewable energy and smart grid. Dr. Chattopadhyay joined the Department of Energy Science and Engineering of IIT Delhi on June 2018, where he is currently serving as assistant professor. Sir, Sumit Kumar Chattopadhyay, sir, you're most welcome to present this topic on multi-level converters for EV application.
Thank you very much for the kind introduction. So yes, it's my opportunity to present today's on today's topic. You can take it as a knowledge sharing session. So I request all of you to participate. And then few of the important aspects on this subject we'll discuss today. So better I keep the video off for better sharing of the bandwidth due to limited bandwidth. And yes, now I'll share my screen. So kindly confirm my screen is visible.
Yes, sir. Your screen is visible.
Right. Okay. So firstly, before going deep into the topic, that's application of multi-level inverters for EV application. I wish that we spend few minutes, and I want all of your kind participation. That what's the motivation, particularly in Indian context, to emphasize nowadays so much on electric vehicle? We say many times that it's about the emission, CO2 emission, and many other aspects. However, I wish to highlight few of the statistical data. So here, if we see few of the statistical data over here, this is the electricity sector in India as updated data available in Wiki. So I'm just using the data available in common source. So here we see that, yes, in the out of total installed capacity of different resources, we have 50% coal, and then around altogether total fossil based electricity generation capacity, it will be less than 60%. However, when we see that the total share of electricity generation based on fossil fuel, that's going to be as high as minimum 75%. So fuel mostly, that's electricity, fuel for electricity, that's mostly fossil fuel in Indian context as of now. If you talk about the efficiency, this is one slide which is giving the scenario. Yes. Any comments here? Okay. So here it is the scenario that in our country as of now, nearly 75 to 80% of the power is coming from fossil fuel. Now, with this data, we can say that emission can really be reduced if the fossil fuel based power plant is going to be more efficient than IC engines used in the vehicles, standard vehicles. But unfortunately, that is not the case. If we see how much is the calorific value of diesel, so we can see nearly 33.7 megajoule per liter of diesel we can get by burning, directly by burning it. And then this is nearly how much? Just as I said, this is a participation based course, or I want to treat this as a knowledge sharing session. So how much megajoule is 1 kilowatt hour? Very simple calculation here. I want you to participate. So that will help me to move faster. So okay, anyway, 3.6 megajoule is corresponding to 1 kilowatt hour. And then we can see that roughly 10 kilowatt hour of thermal energy. And just a statistical data, thermal efficiency of a diesel, of a diesel engine. Okay, here it is not there. I am just telling you. Diesel engine thermal efficiency, we can calculate. Nearly the diesel generators we have that can give nearly 4 kilowatt hour per liter. So that's nearly about 40% of efficiency. Okay. Now, if we see the thermal power plant efficiency, it varies between 30 to 50%. This 50% is actually for very limited power plants where combined cycle is there. Otherwise, Rankine cycle with the temperature and pressure we consider in a thermal power plant, it cannot be more than 36%. And then it involves T&D losses, non-idealities, and then of course the round trip efficiency of the battery, what is involved for the electric vehicle. Altogether, it cannot go more than 25%. On the other side, if I see about the carbon emission, that can easily be found out by checking that subbituminous coal or in between what we have in our country. It's in limited range, we have anthracite coal, so which is having nearly 20 megajoule per kg or above. So from that we can say, if we calculate, just I have calculated few days back, I kept all the data for your reference. We can find out that carbon emission is also going to be same for both electric vehicle and gasoline vehicle or IC engine based vehicle. Then why it is in Indian context, it is so important that we should switch over, we should emphasize to switch over to the electric vehicle. So I wish to see that, briefly, I wish to see that what is your opinion in this context. So anyone can raise hand and give your opinion. What do you think? Anyone? Yes.
Carbon emissions.
Carbon emission, that's what I was saying, that carbon emission, you will see if it is going to deal with same amount of efficiency and amount of carbon that contains in the diesel and amount of carbon contains in the coal of the similar for to generate 1 kilowatt hour of energy. That's almost same. That's what I was saying, that it's neither the efficiency nor carbon emission as of now. If you see minutely the efficiency data, unless there is a major stake of power going to come in near future from renewable energy or hydropower, or even as a matter of fact, nuclear power, carbon emission cannot be a decisive factor. At present context, I'm saying where more than 80% of the energy is coming from, electrical energy is coming from coal-based power plant. Then what else is the reason? Yes.
Sir, it's a running cost.
Running cost of?
Means the running cost of petrol or gasoline engine means that is the highest than the electric vehicle running cost.
Why are you saying so? Because otherwise you would also consider the cost of battery maintenance and all. Battery, I think that is going to be more expensive when it will be time to replace, right?
Yes, sir. Maybe, but right now the thinking of all other like that the running cost is lesser in electric and higher in the gasoline engine.
Running cost, but when it will be considering the maintenance and see the weight of the system, weight of an electric vehicle, the same range is going to be high. Right. Anyway, let's see other opinion. So, Ashish.
Sir, calorific value.
Calorific value, just now I was discussing that almost same you will get. Almost same even in thermal power plant. The efficiency, since it is going through many stages, firstly it will be generated, transmitted, distributed, and the out-trip efficiency of the battery. Then it will be converted to the converter. So all stages, if you consider, yes, of course, the electric vehicle alone may have good efficiency, but if you see the stage from coal to electric vehicle wheel, then it will not be going to be higher than a direct conversion by IC engine. As I said, that IC engine can have efficiency in the range of 35% easily. 40% is a very standard. Right. So there is the question.
Yes.
So, and Rankine cycle, you know that thermal power plant from where mostly the power is coming, it's hardly 36%. And then it will involve T&D losses. Then your round trip efficiency of the battery, then the power conversion loss altogether, right? So what else? Yes, Mr. Umes.
Continuously depleting fossil fuel deposits.
Fossil fuel deposit, yes. That I can also say what fuel we have. Fossil fuel means if you say, that's what I was saying, that unless it comes from renewable, the electricity is coming from renewable, it is not much use in reducing the for emission or efficiency or total calorific efficiency. And what you're saying, the fossil fuel depletion, what coal reserve we have, means proven coal reserve in India, it is 100 times, at least 100 times higher than our annual consumption. That means it can support us easily 100 years. Proven coal reserve, I am saying. Then there are many hidden coal reserve, those will come out. So it is 100 years. We can have, we have the coal reserve. So more time is going, more coal reserve is coming out. Eastern region of the country, we have such great coal reserve. So here lies the answer actually. for your information, India, as I was saying, Indian context particularly, we have huge coal reserve. Immediate effect. In future, of course, when the electricity will be coming from renewable, whatever point you were saying, that is going to be applicable, the emission and other things. But on the other side, right now, the immediate effect, what we can see, even after having lots of power generation or majority of the power generation by fossil fuel, that fossil fuel is coal in India, for which our country is self-sufficient. And from where the diesel or petrol comes from, mainly from the Middle East, right? So dependency of the nation on other countries, that is going to be reduced. We will need to import less amount of petrol or simply less amount of crude oil. That's the reason. Okay, that's the immediate effect. So with this, yes, lots of any question on this? Okay, so this is the motivation. With this, we are going forward. Now, electric vehicles, as we see that, how do we define electric vehicle? So it comes from different ranges, right? So it can be a two-wheeler, right? It can be a two-wheeler. Then it can be a light motor vehicle, like hatchback or sedan type vehicles. Then it can be heavy motor vehicles like electric bus. Then it comes traction. And highest is propulsion, electric propulsion. In all the cases, it comes from a few hundreds of watt or very fractional kilowatt to very small power rating, 2 kilowatt, 3 kilowatt maximum. From there it starts, it comes in the range up to 50 kilowatt in light motor vehicle, then heavy motor vehicle, it comes around few hundreds of kilowatt. And traction goes into the range of megawatt. Few tens of megawatt will come in ship propulsion. All this we can categorize as electrically driven vehicles. Now, what are the components? And where the multi-level converter? As we know, as of now, the multi-level converter, as of now, the conventional concept is that it is mostly applicable for high power. But what else, where else it can fit? We'll see some interesting aspects of it. So firstly, the power converter. That's DC to AC converter. This is going to be used firstly for charging station, charging the electric vehicle battery. For charging a small battery pack for a two-wheeler, even for a two-wheeler or three-wheeler, even for a light motor vehicle, it may not make sense to use multi-level converter. But when it is about heavy vehicles, like few hundreds of kilowatt, there it can make sense. How will come gradually. Traction, of course. But for your information, as of now, in practical applications, heavy motor vehicle or traction, they can hardly use up to 3-level converter, high resolution converter, or the number of levels more than 3 will not be usually observed. However, the opportunity or many of the scopes are opening due to advancement of the development of the devices, interesting properties of the devices that can offer much higher reliability, efficiency, other fault tolerance, and many other aspects. And then we can say that even if light motor vehicle, this single multi-level inverter for light motor vehicle may not be very attractive solution, but multiple light motor vehicle can have battery swapping in a battery swapping stress where batteries will be taken out from the vehicle and placed into a charging platform. So there having such a multi-level converter can be an attractive solution. And of course, for the traction and propulsion. One of the first paper I can share here that has experimentally verified the performance of multi-level converters, asymmetric multi-level converters in vehicular application is here. You can see that this is called asymmetric cascaded edge bridge. What it is, I'll show, but this is a setup. You can see that in a very compact way, this setup was made, and this paper was published more than 10 years back. Now, firstly, what is cascaded edge bridge? As we know that, okay, I can just show it from the slide. So this is called edge bridge. So you can just consider that for presentation here, you can just consider that upper bridge. So you can see that multiple bridges are cascaded. So when S11 and S13, if I say that upper terminal is positive, so we are going to check the voltage with of the upper terminal with respect to the lower terminal. So that will be positive when S11 and S13 are on. And when, of course, S12 and 14 are on, then there will be negative voltage. There is one more point. How we can get zero voltage or bypass this cascaded edge bridge? Suppose we understand that plus VDC or minus VDC1 or plus VDC1 we can get by either connecting S11, S13 or S114, sorry, S14, S12 combination. But then how can we get zero voltage? Suppose we need to connect only two bridges in series and one bridge we do not want to keep in operation. It's a very important and stepping stone concept. How can we have zero voltage? So I want you to respond. I believe that many of you must know this. So anyone? As I have shared the presentation, I cannot see if you are raising your hand. So requesting you to respond directly. How can we get zero voltage here in between this upper and lower terminal of this bridge? In between these 2 points, or in other words, if I want to short circuit this point, these two terminals. Anyone? Okay.
Is it by
Only
operating the
S12.
switches S24 and S22?
S24 and 22.
Yes.
No, I am saying talking about bridge 1, where S11, 12, 14, 13. These are the switches. And what I want,
Only
zero voltage across these two terminals over here, in between these 2 points.
only S12 should be on.
Only S12.
Yes.
How can you say that?
Sir, one of the diode, body diode of S11 and S12 will conduct.
Yeah, but one thing we must remember, when it's an AC, DC to AC converter, so it can be connected to any kind of load. That means it can be operating at any power factor. That means even if the voltage is positive here, the current can be negative. That
Okay.
means even if the voltage is positive, current can be in inverse direction.
There S11 and S12 both.
Yes.
Or
So,
S14, S13.
right, both are correct option. So that is chosen, that option is chosen depending on your heat distribution. In order to distribute the heat between the spaces, either the option S11 and S12 can be chosen, or S14, S10. Both top switches or both bottom switches can be chosen. Right. So in such case, irrespective of the current direction, you will get a zero voltage across its 2 terminals, right? So which switch to turn on, it will not be dependent on direction of current. You do not have to monitor the direction of current in order to turn on a switch. Had the direction of current would have been known to you, then yes, as someone said, it is okay to turn on any one of the switch. That's enough. But current direction is not known here, or even if it is known, we do not want to make the switching dependent on the direction of current. That will need a feedback loop then. We want to make it independent. So yes. So this option is taken of both upper or both lower, and that's applicable to all these 3 bridges. So what happens here? Basically, the voltage, total output voltage, whatever we need, that gets distributed between these 3, and then we get, instead of 3 level, we would have got with a single bridge, that's plus VDC1 minus VDC1 and 0. Now how many levels we can get? We can get, assuming that all 3 voltage VDC1, VDC2 and VDC3, these are at same level, we can get total 3 positive levels, 3 negative levels and 0 voltage, total 7 levels. So that's how the simplest multi-level converter comes here. But for the edges, we use 2-level converters. Suddenly, what is motivating us to switch over to multi-level? So that's the point of interest, and that's true for the electric vehicle application. So for this again, I wish that all of you participate. Let's see a 2-level inverter. So how do we represent a ideal 2-level inverter? So what we do? We have a voltage source, so VDC, and then we have a switch. That's basically single pole double throw switch, ideally. So at the output, this output can be either clamped to this positive terminal or negative terminal. But then at the output, what we need, nearly sinusoidal voltage. So what we do, we call it pulse width modulus. Very briefly, we'll review it in a very different way. And I want all of you to participate. For now, you just forget that we are discussing here pulse width modulation or any electrical circuit. Just go with the discussion. Assume that here we have a rectangle arbitrarily taken rectangle, and this is a straight line. Just forgive me and consider that this is a straight line. This is a diagonal. Okay. And on this diagonal, any arbitrary point I'm taking, this is the arbitrary point. Okay. And above this arbitrary point, I'm drawing one horizontal line and a vertical line. So now I need your comments. Can anyone comment on the area of these two rectangles? There are total 4 rectangles. I'm just asking about these 2 rectangles, what I have marked here with hatch. Is there any relation between these two area of these 2 rectangles? Anyone can find it out? Very simple, +9 geometry. All comes from the properties of triangles. Anyone? The relation between these 2 shaded areas. Remember that this is an arbitrary rectangle on which diagonal is drawn, on which an arbitrary point is taken here. It could be anywhere, here, anywhere it could be. So I have taken it here, and on which I have drawn a horizontal and vertical line. So it forms 4 rectangles inside. So I'm asking about the area of this 2 rectangles. Any relation is there or not?
Same.
Yeah, then why it is same? Yes, you're
I
right.
did a calculation. Means I
You don't
assumed
have to-
some values and from that I did calculation.
You don't have to calculate anything here. It's just observation. See this rectangle. Okay. Here, this area is same as this area. Then this rectangle on which this is, so this triangle is same as this triangle. And of course, this bigger triangle, this area is same as this bigger lower triangle. And what we are doing from this bigger triangle, these 2 smaller triangle we are subtracting in both the cases. Right? No calculation is needed, only observation. So these 2 areas are same, from which we can say that this shaded area, this shaded area will be same with this shaded area will be same with this shaded area is going to be same with just 1 minute.
Sorry, sir.
This area, right? And this is a very basic essence of this pulse width modulation. What we are doing here, this is the triangular carrier. Okay, though here it is like a sawtooth web. This gets continued for multiple cycles. So this is the sawtooth wave, and at a given instance, this is the reference. And what we know, if the reference is above the carrier wave or higher than the carrier wave, the switch, there is a comparator, then that switch turns on, or that switch connects to this plus VDC. So what will happen? It will turn on the switch and the voltage will be clamped to this positive value. And when the reference wave comes below, then it becomes negative or this clamps to 0. So observe that this blue line was the reference for which this was the area of the triangle, sorry, rectangle. And now it is turning on the switch during a given instance. And as a result, what is happening? Net area, volt second area for this time duration, Ts, is becoming same between the reference and output, even if the magnitude is not same. However, and then what is happening? If there are many such carrier waveform. Okay, before that, one more thing I can say. This same concept would have been applicable or valid even if I would have drawn the diagonal from the other. Then also this same concept would have been valid. So from that, we can conclude that whether it is a sawtooth wave or a triangular wave, finally, the pulse width modulation will be applicable. Though in triangular wave, it's not only easy to generate a triangular wave compared to a sawtooth wave in a given analog circuit, but also the accuracy is going to be more with a triangular wave. The reason I am not discussing now. So you can say the triangular wave is having two rectangles, where I have drawn these two rectangles. And then when I'm passing the reference, assumption is that the reference is not changing much within this time period. And whatever change is there, that actually induces some kind of error in the circuit. So that actually results into non-idealities or harmonic components as well. So yes, having higher frequency of switching. Now here in this diagram, we do not have any option to make bipolar voltage. If I connect the load between any of the DC bus and this output, the voltage will not be bipolar. So here we can assume that bipolar voltage is going to be generated with respect to a midpoint. So each of the capacitor, these are the capacitor, each of them are at voltage VDC by 2. So plus VDC by 2 and minus VDC by 2. So when we connect the load in between, but for the three-phase system, you can see that this virtual neutral is not connected. Simply because the line-to-line voltage that finally appears to the load, right? So for just a single phase analogy or analysis, we're assuming that this load is connected in between this midpoint and here. Now, with this, if we go for high frequency, of course, the output voltage can be close to lower order harmonics will not be there. Higher order harmonics will be there, which can be easily filtered out because of the coupling inductance or filter. If we have inductive filter here, or some inductance is there in the filter, so we know the impedance of filter is omega L. So of course the J term, I'm just talking about the magnitude of the impedance, not talking about the phase shift. So if we analyze the output voltage, PWM output voltage, that has lots of harmonic components, but those are higher order harmonics where omega is very high, so they observe very high impedance that gets filtered out. That has negligible effect. However, it has several disadvantages, like this switch is continuously switching between class VDC and 0, and that too at high frequency. So it induces good amount of or high amount of switching losses, as well as a bigger or significant size of the filter is needed. Also, having a two-level converter for high power applications or like high power drives, that invites many other limitations, like high rate of change of voltage, as we see that the voltage is falling very sharp or rising very sharp here. So DVDT is very high, in the order of 5 kilovolt per microsecond. This is as high as 5 kilovolt per microsecond. So that causes leakage current, as well as high DVDT may cause premature failure or premature aging of the insulation of the device connected with, say, electrical machine, whether it is a transformer or rotating machine. So other than that, electromagnetic interference, loss actually also brings a question on reliability, because more is the loss, more is the heating. So altogether, and that heating actually not only reliability, it also demands derating of the devices. For example, you want to operate a device, say for example, 800 volt. Just one example is I'm giving here. 800 DC bus. This DC bus is 800 volt, and we want this current RMS current to be 50 ampere. Okay. If we want to operate this at a frequency, say 20 kilohertz, you can calculate. There are softwares. Any idea if we are managing this with a 1200 volt IGBT, what will be the current rating of the IGBT for such frequency 20 kilohertz? If we want to limit the temperature to a decent level, that's below 100 degrees Celsius, with a forced air cooled heat sink, what could be the current rating of this IGBT? Anyone? Any idea? Of 600 ampere. Pardon? So 600 ampere. And why this 600 ampere? Because it requires significant derating to accommodate the heat. Now, why 20 kilohertz? Of course, what power quality can be available with 20 kilohertz that we can easily get with a multi-level converter where final volt ampere rating will not be this high. Another advancement or another concept which is very much going to be used in near future to bring modularity, as we see that the electric vehicle. So those are the storage is battery storage, the battery pack. So individual battery pack, how much is the voltage? The order of 12 volt, right?
Yes, sir.
Yeah. Now, let's see something very interesting here. If we see the characteristics of devices, here it is. A MOSFET, if we consider this blue line, you may consider a very range. Suppose there is a 100 volt MOSFET that can be easily used for maybe 24 volt receivers, even for 48 volt receivers. So that has a on-state resistance of nearly 0.06 ohm, right? Now, if we take 1000 volt, which is 10 times higher, we see that the forward drop is for the same chip area, it is more than 100 times. Voltage, breakdown voltage is 10 times higher, blocking voltage is 10 times higher. And for same chip area, the resistance is 100 times higher minimum. 100 or 200 times higher. Of course, for that at high voltage, IGBT is used like this, what you can see. But even if you consider IGBT at 800 volt range and a MOSFET at say 50 volt range, it will be differing by nearly 100 times. So yes, but MOSFET, it is not recommended to connect in series. Why? Now in this class, I cannot discuss in a short time. But then if we could have connected 10 MOSFETs of 100 volt in series or 20 MOSFETs of 50 volt in series, that would have much lower conduction loss compared to a single MOSFET or even single IGBT of that voltage rating. But instead of series connection that demands very high power, very specialized gate drivers, we can divide, since we have much smaller voltage battery packs, we can divide it in multiple parts. And that finally gives this concept that cascaded edge bridge that can bring modularity, and this bridges can be replaced or realized with a MOSFETs. And not only that, this, when we break this into multiple parts, this can also, up to some extent, it can offer active battery balancing without additional circuitry. Any question on it? The power distribution between VDC1, VDC2, VDC3, etc., that can be adjusted by depending on how much time duration a given amount with a given cascaded edge bridge will be operating to generate a voltage level. Okay. Again, cascaded edge bridge, here we can see that it has only option that we can have a battery bank can be distributed, and this can have application in many places, starting from traction propulsion, definitely propulsion, it has been proven. Multi-level high resolution multi-level converter has made its path already. And other than optimizing the conduction loss in this way, having low voltage cells realized with low voltage MOSFETs, it can also be seen that since there are more number of levels, requirement of switching frequency to generate power quality, generate a given power quality, that reduces. Why, again, I cannot discuss right now. Just an example I can give you. Suppose there are 20 cells. 20 cells of 16 cells, 16 cells of 20 kilovolt. Or I can say that 16 cells in a model multi-level converter, 16 cells per arm. So that can give you 17 levels at the output phase voltage. So with 17 level, what power quality you can generate with nearly 150 hertz switching per cell, only 150 hertz. 150 hertz per cell, it is switching. And there are total 16 cells per switch, sorry, per arm. That can give an equivalent. If you want to generate same power quality with a two-level converter, the switching frequency would have been in the range of 30 kilohertz. Okay. So there is something called frequency multiplication that I'll show if time permits. So that happens in both multi-level converters and cascade converter. So other than optimizing the switching loss and conduction loss, also we can say that if one of the battery pack fails, we can permanently bypass it. So it adds to fault tolerance. Moreover, one more very important aspect now I wish to discuss about the filter losses in the filter. Suppose a PWM waveform we are generating with a two-level converter. Say phase voltage, I am just denoting at this phase voltage VPH, a two-level converter. So plus VDC and minus VDC in between, it is varying. So gradually it will look like this, a positive half cycle. So on, this will be continued. So observe that suppose the output is plus VDC by 2 here, as per the diagram I have drawn, and here it is minus VDC by 2. Any comment? What will be the RMS value of this waveform? This waveform is always varying between plus VDC by 2 and minus VDC by 2. What will be the RMS value of the waveform? Yes, anyone? RMS value of the waveform will be how much?
Positive only.
Yeah, positive only. And magnitude?
VDC.
VDC by 2.
VDC by 2, right.
Either plus VDC by 2 or minus VDC by 2. So it's finally going to be VDC by 2, the RMS value. Now suppose it is containing a fundamental component for which the peak magnitude is VDC by 2 again. So what is the RMS value of this? VDC by 2 root 2 times less, right? So this is an indication, and this voltage, if this voltage, this kind of PWM voltage that appears in a magnetic component, finally, the loss components, if we analyze, there will be effect on hysteresis loss and eddy current loss, and how it will be, we're trying to find it out. Eddy current loss is finally, it occurs because there is induced EMF in the core, and depending on core resistance, the eddy current is developed, right? Now, what we observe, then it will definitely depend on RMS voltage induced on the core. So in which case it will be more, whether it is a sinusoidal voltage or it is a PWM voltage. If we directly compare a sinusoidal voltage to a PWM voltage, in one case it was VDC by 2, and for sinusoidal it is VDC by 2 root 2. So from here we can say apparently, approximately, the eddy current loss is going to be double, irrespective of the core, for the PWM voltage, if you compare it with its corresponding fundamental component. Moreover, depending on the frequency, the local hysteresis size of the local hysteresis loop, that is that depending on the ripple current on the top of the ideal current or harmonic current component, the local hysteresis loop's area will determine what will be the effect on its eddy current losses. But in a nutshell, we can say definitely there will be a significant difference in the specific core loss. And not only on the specific core loss, that's the core loss per kg. Not only that, since the harmonic components are not there, higher order harmonic components are not there, we can significantly reduce the filter size. So size of the filter for the multi-level inverter where the output voltage could be closely approximated like a sine wave, there the output voltage, because of that, not only the filter size is going to be bare minimum, also specific core loss will be reduced. It has twofold effect. On the other side, also we can say that when we have high frequency switching like this, it requires a special core. A normal CLGO core cannot take care. When you have a closely approximated sine wave, due to high number of levels at the output, like what is shown over in this paper, a kind of output you can see here. There, you can say that the since it is very close to close approximation of the sine wave, the normal CLGO core itself can be sufficient to serve as a filter. So it has not only its impact on switching loss or core loss, switching loss or conduction loss, also it has its effect on the filter losses. So other than that, DVDT stress, rate of change of voltage with a PWM, high rate of change of voltage for a larger duration, that finally induces leakage current between the interwinding capacitance, and moreover, not only between interwinding capacitance, also in the cable insulation. So that actually results into premature failure. So low voltage switch using low voltage switch, we realize even for a low voltage application, like what we can see a few 100 kilowatt or 200 kilowatt range in an electric heavy electric vehicle, such converter concept can lead to an attractive solution, like what we can see that even an asymmetric converter here, that was also giving a I would say it was giving a good challenge to a two-level converter, even in this power range of a light motor vehicle. Of course, there are many limitations. Now, one quick question here. What we were discussing in the PPT. Suppose these three voltages are having equal voltage. So we can get 7 levels. So total 3 positive level, 3 negative level, and 0 voltage level. Now suppose if we make it unequal, suppose this is V can be say 100 volt or anything. This is 3V and this is 9V. How many voltage levels we can get at the output? There was a maths puzzle used to be given in our childhood, that you have a 40 kg stone. If you remember this, or if you have done this, 40 kg stone, you break it into 4 pieces, such that using those 4 pieces, you can measure any weight from 1 kg to 40 kg in a resolution of 1 kg. Is 1 kg, 2 kg, 3 kg, up to 40 kg. So how this 40 kg stone will be divided? So anyone solve this problem in school? The solution is 1 kg, 3 kg.
Too much you know.
Yes.
And
And 27 kg, right?
right.
So what is the ratio? It's a trinary ratio. And why it is happening? Say this is 9, this is 9. Now from here, this is -9, here this is 0, this is +9. Now I put 3. So we get equal distance, right? And again, if we put this is 3 and then we put 1, again we get equal distance up to this, and so on and so forth. So with limited number of switches, earlier say with using this same structure, 3 edge bridges, we were getting 7 levels. Right? Now we will get how many levels here? Help me to find out. Anyone? There will be 27 levels. You add one more bridge, there will be 81 levels. To be multiplied every time, it will be increased by 3 times. But anyway, it's called asymmetrical inverter, but it has, though it looks attractive to make a generate a very high power quality, but it has other challenge that personally I'm working on. Actually, the challenge is that these two auxiliary sources, so this is 9V, this is the main source, and this 3V and V are the auxiliary sources. So these two auxiliary sources handle very small amount of power. More than a, pardon? Yes?
Addressing no, sir.
Someone is saying something? A very small amount of power will be handled by these two sources. So that's finally going to cause this topology to lose modularity. And moreover, in some time, it may happen that when you are supplying power outside, this low voltage bridges will be absorbing power. So for that, actually, in this paper, some work was reported where it has actually using high frequency link. This is the main power source, which is going to supply to the main bridge. And other than that, it has high frequency links. So through those high frequency links, these auxiliary power sources have fed and the output voltage is generated. This high resolution output voltage, which can be closely approximated as a sine wave. But again, this close approximation, this disadvantage remains when it operates at higher modulation index. As the modulation index reduces, the peak magnitude will reduce, the number of levels will reduce. So a combination of PWM and this nearest level control will be required to maintain power quality below a particular modulation index. But anyway, here they are in this paper, they are operating, as I said, that this power distribution ratio are very small. So the target is that there will be no dedicated power supply or battery for this auxiliary sources. Those will be fed by the main source only through a smaller isolated DC-DC converter. Bidirectional and to avoid bidirectional converter, what is done here, you can see they have again used a buck converter in between, bidirectional converter in between, because in a particular modulation index they have operated. It was not a variable modulation index because the power distribution ratio it was found. The auxiliary source, as I said, it can be sometimes negative. This is the power distribution ratio, percentage of or amount of power. Sorry. Yeah. So that finally varies between positive and negative. So it has identified some modulation index in between 0.783 and 0.796, where the auxiliary sources will be handling minimum power. But if we want to change the output voltage, but without changing the modulation index, the only solution is that we should vary the DC bus voltage. So that's what is done here. And with this, they have driven an electric vehicle. But other than that, this outcome is significant because this has explored many of the cherished advantage of the high resolution converter. However, there was scope to improve the number of levels further with the same number of switches or to avoid any such auxiliary sources like this. So those I am not going to discuss in this conversation or this knowledge sharing session today. However, rather I prefer that other than this, a very important topology is modern multi-level converter, which can be used, which is already in use for the ship propulsion or high power applications like traction, or also battery swapping station. It can be useful. Though cascaded edge bridge can be a good alternative to MMC, MMC is not required at all if you just need to interact between the battery and the output AC side. When you actually need a 3-port network, basically 3-port power network. That means in MMC, what you are getting, if we have inside each submodule, if we have battery, whether it is inside a vehicle or in a battery swapping station. In all cases, these receivers will be unutilized. And in such case, the same output could have been managed with a cascaded edge bridge. When this DC link is open or unutilized, in such case, MMC is nothing but a combination of, you can say, it's like parallelly connected, two parallelly connected cascaded edge bridge, cascaded hub bridge. Okay. So how it will be, that again I'll discuss later. After this, rest of the time, I'll go detail into the operation of this topology. Actually, I guess for the completeness, I thought of discussing the working principle of both other two topologies, important topologies, potential topologies for EV applications, whether it is for the battery swapping station or inside the vehicle or in a propulsion or traction application. But what I understand that most of you will be well aware of the operation of these two topologies, that's neutral point clamp and cascaded edge bridge. So to save time, this is most important, which is gradually coming to surface, the operation of modular multi-level converter. So here we will take a short break, and before the break, I need your opinion that it will take some time to discuss the modular multi-level converter, which is expected to be relatively more challenging for everyone. So should I directly discuss that, or for the completeness, I should discuss the working principle of CHB and NPC converter also, cascaded edge bridge and neutral point converter also. So organizers can give their kind opinion. After this, we'll take a 5-minute break. Anyone? Do you want me to discuss CHB and NPC also, or directly I should enter into the working principle of modular multi-level converter, where more challenging aspects are there corresponding to its balancing and operation?
We can take a break, sir, sure.
Yeah. After break, I'm asking that should I discuss this cascaded edge bridge or NPC also, along with MMC, or solely focus on MMC? Because MMC has lots of more technically intensive aspects to understand there. And particularly those are not written anywhere. Those are from my understanding. Yeah. Yes. Mr. Yeah.
Yes, myself is Ram Dekekar
Yes.
from Maharashtra. Sir, my
Yes.
question is any aspect related to the level, sir, which affects the performance, like 9 level, or we can say go higher level, 11 level?
See, more number of levels we are going, it is becoming close approximation to the sinusoid.
Sinusoidal, right.
But at the same time, how many levels we can go where it ends?
Right.
That's going to be finally restricted by the improvement in the power quality.
Right.
Finally, the THD or is 1% or THD is 0.5% hardly matters finally. So whether we need whatever improvement we could have done with 27 levels at the output, so it may not make sense much, or say even with 45 levels at the output, Then further, if we go for 101 levels at the output, or 200 levels, 201 or 251 levels at the output, it will not change much in the output side in terms of performance. On the other side, the converter implementation cost will go up. Yes, still 250 level or 251 level inverter is there in operation, in practical operation, but that is not for such low voltage. That's for HVDC application. Generation 5 HVDC converter station, or based on voltage source converter manufactured by ABB, they do have very high number of levels on HVDC plus by Siemens. They have such high number of levels, but that's not for increasing the level due to restriction on power quality. It is because availability of the devices. So 500 kV is the DC link, and then the converter is going to be realized with the switches that can support 2.5 kV of voltage, DC voltage, right?
Right, sir.
But here in this case, suppose we are operating for low power, then also we are getting one motivation to increase the levels. Yes, high number of levels has lots of advantages, as I discussed, but it is also realizable because it's fed by battery, and then battery bank can be divided into multiple distributed modules, so it can optimize the switching loss, conduction loss. It can also offer active battery balancing. So this discussion, I'm saying, this discussion is going in context of medium or low power. But when we consider plus 11, medium or low power, sorry, for the lower voltage. But again, from the context of very high voltage, like 15 kV, or even, as a matter of fact, 6 kV drive, MV drives, their multi-level inverter is a very well-proven, well-known topology. So cascaded edge bridge and NPC, in order to reduce the losses as well as to distribute, because otherwise there you do not have the available switch. So
Sir,
if you don't,
okay,
yes.
okay, sir. My second question related to this for high voltage.
Yeah.
For high voltage, if you have the frequency modulation index is higher.
Yeah.
So is it possible to switch that much of voltage to that frequency practically?
No, we do not switch.
Like 500 kV voltage, suppose we are switching to that much of frequency, kilohertz.
No, not offer at 500 kV system at such high frequency, first of all. And I never mentioned it. I don't know why you were mentioning, but
it was the questions during my defense for that is the high voltage switching.
Because it is not possible, first of all, leave about 500 kV. Even for a 6.5 kV IGBT, which is maybe can be connected to 4.5 kV DC bus, that's not recommended to operate beyond 500 Hertz switching.
Right.
Okay.
And okay, sir. Thank you. Thank you. So practically it is not possible to switch that much of voltage.
Yeah. And there the motivation for multi-level inverter comes. Suppose you leave about 500 kV. Suppose you have switches that can support 2.5 kV DC bus. Okay.
Right.
Now you need to handle the DC bus of 10 kV. So if you have such switch, you need 4 switches to be connected in series.
Right.
And then that has to be operated, suppose at maybe at 5 kilohertz, which is not possible to achieve. As I said, 500 hertz is the limit. On the other side, you divide the switches into the DC bus into 4 parts, 2.5 kV each. So in cascaded edge bridge, say you have 4 cells. So what will happen? each are operating at 2.5 kV.
Voltage
So you do
reduce.
not need any series connection.
Right.
And moreover, having multiple levels, that reduces the need for high frequency switching. That 5 kilohertz, what I was discussing, that 5 kilohertz will be coming below 500 hertz maybe. I'm not so sure, I'm not calculating, I'm just giving you an example. So increasing the number of levels by having phase shifted PWM also reduces the need of number of switching, because there is used to be frequency multiplication that I cannot discuss in such short time. You may contact me later if you have curiosity. I can explain you. Okay.
Okay, thank you, sir.
Here is some phenomena we understand as frequency multiplication.
Right.
So how it happens, we can see with some simple simulation at later stage. Right now, I can show you something over here. Let me see. A phase shifted modulation example, if I show you.
Sir, I worked on carrier phase shift
Yeah, here
modulation.
it is. Suppose here, say 0.75 is the reference. So the upper triangular carrier, if you consider, which is phase shifted by 90 degree. So you observe, if we add this blue voltages, which is varying between 0 and 1, what is happening at the output? You are getting always 3V voltage. Whereas there is a switching happening here. So taking the advantage of this thing itself, there can be something called frequency multiplication. Had this been instead of 0.75, it would have been 0.8. Then there would have been pulses what would have been varying in between 1 and 4V and 3V. And then we would have found 4 pulses within one cycle of the carrier. So that's how the frequency gets multiplied other than adding the number of levels. Anyway, that discussion is going to take much longer time. So we'll discuss it later if you are interested. Any other question? Okay, I'm just asking the organizers, may I get 5 minutes extra time?
Yeah, yes, sir. You can take, sir, please.
So instead of 5:30, maybe I have to continue up to 5:35. I'll take just a couple of minutes break. You may list down your question. Once I come back, I'll let you know. You may ask 2-3 quick questions, then I can switch over. And as you are not giving your opinion, then I am taking my decision. NPC or CHB are up to much extent it is self-explanatory. So I'm not going to discuss now. Rather, I prefer to discuss which is more challenging. Okay. So I'm just coming back by 2 minutes. Yes, I am back. You may have, if you have question, you may ask 1 or 2 quick questions before I enter into the other topic. Okay. So I guess I can. We'll study this MMC. We'll try to understand the working principle of this modular multi-level converter. Some very basic principle. As we know that for high power handling, particularly when we have the requirement of 3-way power flow, particularly the submodules connected with the battery bank. So suppose, for example, battery swapping station, which may be fed from a DC side, which may be coming from the renewable, and also from the AC side. So MMC is going to be a very attractive solution. So many such proven applications are there. It's better to have a look on this, look into this. This SMs are the submodules. So this can be a hub bridge or full bridge. So in this discussion, we'll restrict our study to hub bridge only. And then what we are defining, this we can see this is the output VA, VB, and VC. At the upper side, there is a inductance and series of submodules. So this we are calling it upper arm, and then this inductance, that's why it's called arm inductor. And this is called, the lower side, it's called lower arm. And upper arm and lower arm together, this is forming a phase leg. This is the leg corresponding to phase A, similar to phase B and phase C. How we can get the output voltage, first of all. And then secondly, it comes as a concern that if this submodules are fed by capacitors or even battery, how they will be balanced? They will be fed equal power or the power as per the requirement. Or power handling through this DC side or AC side. So we'll come to a very basic circuit first of all. Assume that there are 2 voltage sources. Forget about MMC, just a basic circuit here. These 2 are fixed voltage source connected to this ground point. So plus V and minus V connected here. And these 2 are the variable which can vary its variable voltages, which can vary its voltage 0 to 2V. So presently say these are at a voltage V. So at such situation, if we apply Kirchhoff's voltage law here in this loop, we can see that here 2V is the voltage and this side also 2V is the voltage. There will be no current. As I said, this voltage is a variable voltage source. So there will be no current flowing in this loop, as well as since this voltage is at V and this voltage is also V, and this resistance from now we are considering as a load. The other side is connected to this ground point, return path. So there will be no current here. This point potential will be exactly same as potential of this point. Now, if we differ the voltage of the upper arm reduced by an amount minus delta V and added by an amount in the lower arm plus delta V, still you see the Kirchhoff's voltage law is satisfied here. This is V minus delta V and V plus delta V. It becomes total 2V, and here also it is 2V. However, we observe potential of this output point where the resistance R is connected, that will be at plus delta V with respect to this ground. So this delta V can vary in any range depending on that its output voltage changes. This is the very basic essence of generating output voltage in an MOC. So equivalently, if I consider this circuit, equivalently, see this is plus V, and from that V minus delta V subtracted, so effectively it becomes delta V, like this, delta. Similarly for the lower side. So effectively two delta V sources parallelly connected. So output you are getting here, delta V. Whether it is a resistance or an impedance with a back EMF, in all cases, this voltage is delta V. This back EMF and impedance together will determine what will be the current flowing over here. What is the magnitude of current going to flow here? Now, that current, since it will observe equal voltage at two sides as if two parallel voltage sources are connected, if we neglect the non-idealities, then this current is going to be equally distributed in upper and lower arms. What is arm? We have discussed here. This is arm. This is the arm. This is upper arm. This is the lower arm. So whatever current is entering is going to be distributed equally the upper and lower side. But it has a different implication. Observe that in case of upper arm, current, this current AC current component, when the current is inwards, current is entering from the bottom side and leaving the top side of the arm. But for the lower arm, for the same direction, for the positive, when the current is inwards, current is entering from the top side and leaving the bottom side of the arm. It will have different implication in its opposite. We'll see it soon. So what should be the range of these variable voltage sources? As we are saying that this is the variable voltage source. This is the variable voltage sources here, which is basically the arms are basically acting as this variable voltage source. So what should be the magnitude of voltage these voltage sources have? What should be the range? that actually going to determine what should be the range of variable voltage or voltage required for those amps. Observe, when we wish to clamp this output resistance to this positive DC bus, what will be the magnitude of UVP? Participate with me. When I want to clamp this point to this positive DC bus, what will be the voltage at UVP? Unless you respond, it will be very demotivating for me to continue. It's so simple. This point is going to be connected here. We want to connect this point over here. So this variable voltage, how much should be the voltage here? Am I clear? Is the question is clear? Am I audible?
Yes, sir, you are clear, sir. You are audible.
Okay. Yeah, anyone can respond?
Sir, audible.
V minus U naught, sir.
I
Difference between
want
input and output.
no. What I'm saying, I want to clamp this point to this DC bus. So what should be the magnitude of voltage UVP? It should be 0, right?
0.
Then only this can be directly connected here. It is in between. It has to, this output voltage has to adjust to 0. Then only this point is going to be connected here, right? So in such situation, if this point voltage is 0 and consider the loop over here, KVL, what should be the voltage of UVN? KVL has to be satisfied. Here it is V and this is also V, and this is 0. Then UVN will be UVN has to be 2V, right? Then only the KVL is going to be satisfied. Similarly, if I want to clamp this voltage, output voltage to negative DC bus or minus V if I wish to have, UVN will be 0 and UVP will be 2V. So this determines, these two worst case situation determines the worst case voltage needed or maximum voltage needed, sorry, minimum voltage needed to stay connected or to develop a given voltage at the output. So here is a waveform given U0, which is varying in between plus V and minus V. And then for that, are you saying something, Louis? I request you to mute yourself.
We request participants to please mute your audio.
Yeah. So is plus V and minus V. This is the output voltage U0. This is U0, right? This is the output voltage U0. So it's varying between plus V and minus V. We used to vary. Naturally, the same with a what happens with a two-level converter. We represent this as plus VDC by 2, and this is this side also plus VDC by 2, so that here we get minus VDC by 2 when this side is connected. So that thing we have written here as V. Now, corresponding voltage for this upper arm and lower arm is given here. So we see that upper arm voltage is 0, as I said, when plus V is needed, or we want to clamp the output to positive DC bus. And 2V is needed when we want to clamp the output to negative decibels and vice versa on the other side. And always observe the sum of this upper and lower arm voltage is 2V, right? So that's how the KVL is satisfied in this loop. And output voltage over here, that's going to change. It's not necessarily to be sine wave again. It can be any other kind of wave. But in an inverter, a DC to AC converter, considering the output is supposed to be sinusoidal. Now what will happen, as I said, notice the direction of current. When the direction is outwards, I0, that time the IP and IN. IP is the current in the upper arm, AC component of the current, and IN is the AC component of the current in lower arm. And that we understood by magnitude. We, from the discussion in the earlier slides here, we understood, as we discussed here, that this AC component of current is going to be I0 is going to be equally distributed. That is, magnitude of IP is nothing but I0 by 2. Similarly, IN is also I0 by 2. However, you notice the direction. As per KCL, these directions will be like this. Now consider the polarity of UVP and UVN. When the current is outwards, instantaneously it is outside. Then with this magnitude, with this direction of IP, what will happen to UVP? It will charge or discharge. With this direction of current, notice the polarity of UVP. It will charge or discharge?
Discharge.
It will discharge. See, current is going this direction.
Charge.
And
Okay, drop in potential. Yeah.
Yes. This is charge, right?
Yes.
This is
Charge.
positive. And here, this side is positive, and this is the direction. So this will be discharging, right?
Yes, sir.
Yes.
So
Yes,
upper
sir.
side is getting charged and lower side is getting discharged. Similarly, when the direction will be changed, then lower side will be charging, upper side will be discharging. But what is the amount of charging and discharging for a given current? Let's observe. So let's check this IP. Let us check, consider that this is a resistive load. It will happen, similar thing will happen for a non-unity power factor. But for simplicity, now keep it consider a resistive load. So this is IP, the direction. With that direction, if I say that this is a charging instance, so of course, here the current voltage is always positive. Current polarity has changed here in the other cycle. So this must be the discharging instance. So charging is more or discharging area will be more. Total volt ampere product, volt ampere second in the first half cycle, which is for charging, that will be high, or the second half cycle discharging, that will be high. You observe when this current is maximum, this voltage is 0. When this current is negative side maximum, this voltage is also maximum. Here lies the hints. For all other corresponding point, you can check. So charging will be more or discharging will be more?
Be more. Discharging will be more.
Yes.
Discharging will be.
So discharging.
Right. Similarly, for the lower arm, for UVN, this is the output voltage. And as I said, when upper arm is charging, lower arm is discharging, and vice versa. So again, lower arm is also having higher amount of discharge. So in overall, over a cycle, you can say that even if there are charging instances in both upper and lower arm, however, over the cycle, both upper and lower arm will be discharging. If the system is supplying current outside or supplying output current is feeding a load. Or I mean to say the load is positive. Okay, both are discharging. What about a leg? Leg is also always discharging because a leg is the sum of this upper arm and lower arm, and we understand that discharging is always more than the charging. So if you add them up together, discharging is higher. That means as of now, if we consider that this is an ideal circuit, these are the ideal sources, and these voltage sources are also ideal. In such case, only AC current is flowing, and that AC current is passing through these two voltage sources, DC source. So DC source, in a DC source, if AC current is passing, what will be the net power handled by the DC source over a cycle? It will be 0, right? It will be 0. So whatever power has to be handled or supplied to the load, it is not coming from this DC sources, this ideal fixed DC sources. These are coming from this variable ideal sources denoted as UVP and UVN. Okay, because this current, what it is causing, that current is actually AC current, and that's causing these two sources to supply. Or had this been implemented with a capacitor, then those capacitors would have been discharged. So what will be the effect of that discharging? Say, as I'm saying, UVP and UVN. Now I'm directly writing these are the two V and V. So as I discussed, this is 2V. Now I'm replacing with a single cell modular multi-level converter. Nobody implements a modular multi-level converter with a single cell in a given arm. This is only for your understanding. So what we understand that there is no source, and we understood that both upper and lower arm, they are supplying power. That means these capacitors are supposed to discharge. When they will discharge, it will become less than 2V. This will also become less than 2V. Will it be possible to maintain Kirchhoff's voltage law in this loop without having a DC component of current? No, because sum of this voltage and this voltage will no longer remain 2V. Earlier, either when it is an ideal switch, when this was in the circuit, this is removed, or this is in the circuit, or here 2V, here it is 0. But now these two capacitors are discharging, and then the voltage is getting deviated from 2V, less than 2V. And assuming that the stray resistance of this path is going to be negligible, very small amount of deviation in voltage would have caused very high inverse current. To limit that, now we have provided this inductors, arm inductor. You can see in the equivalent circuits before, here in this or this diagrams, I have never drawn the inductor before. Now, for the first time, I am drawing it here, because now I understood that these are not voltage sources, these are capacitors. Voltage is falling down, so it cannot generate a sum of these two upper and lower arm voltage cannot remain 2V any further. It will be less than 2V in such condition. And if it is less than 2V, then This side it is 2V, and this two voltages together in this loop is less than 2V. So this will start a DC component of current to flow. Earlier we have seen the AC component of the current was getting distributed like this. Now in addition to that, as the capacitors are discharging, a DC component of current will start flowing. So this arm will have both AC and DC component of current. When you consider this is a three-phase system, then this AC component of currents, they will be circulating within the three phases because some of the three-phase currents are zero. So three AC currents, some of them will be zero. So this DC source will have only DC component of current. There can be some ripple that will be corresponding to the voltage ripple of these capacitors, not corresponding to the AC component of current. That's going to cancel out within the phases. Okay. Any question up to this? All right. Now, as I said, it was for your understanding. Nobody implements MMC using only one cell per arm. But anyway, if I ask you that how many levels we can get at output with this thing, with the corresponding discussion we had so far, that either we have to turn on this switch, means either we can have we have to have 2V here, or we have to have 2V here. When it is 2V, this side is 0. When this is 2V, this side is 0. So in that way, how many levels at the output we can get them? How many levels we can have?
5 levels, sir.
Pardon?
5 levels.
How you will have 5 levels? When you turn this
upper 2.
See, we have only two combinations. When this is 2V at the output, this has to be 0. And that time, this is clamped here, this side. And when this is 2V, this side is 0. Then this is clamped this side. Only 2 levels. And that's why I was asking the question. It's not 5 levels, it's only 2 levels. Mute yourself. Yeah. I have not discussed so far that there is also option. You can make this also 2V and this also 2V. In such case, this inductor will be acting as a potential divider. In such case, you can get 3 levels at max, not more than that. So this is a 2-level MMC. Now, if we see that what happens, as I have shown earlier, this is the lower arm voltage, and this is the lower arm current. So which is together, it is causing a discharging area up to this. This is the discharging area. Any question? If you are not asking question, then I'm requesting you to mute yourself.
Participants, please mute yourself. Participants, please mute yourself.
Thank you. Yes. And on the other side, if we see on the other cycle, this is the area when the charging is happening, and this charging area is really smaller compared to this discharging area. So this is the amount of energy or power instantaneous. This is the instantaneous power handled. So this area is the energy. The integration of the instantaneous power that gives the final amount of energy handled. This is shown over 2 cycles. If you multiply, it's assuming 50 Hertz, multiply it by 25. So you will be able to find out what is the power in watt. So we can see that as we are integrating up to this instance, the integrator keeps on rising and then it starts falling up to this. Again, it is rising up to this instance as this is positive. So this is the net amount of energy handled. Energy delivered by the source. So naturally it will discharge the capacitor. This simulation is done assuming that the capacitors are ideal or with infinite value, or those are not capacitor, ideal sources. So these are finally delivering power. But it cannot do that. It's a practical capacitor, it will discharge. And what will happen? It will have DC component. What is the effect of this DC component? You can see the current here. If we add some DC current of proper magnitude and direction, the current waveform that gets an offset, DC offset here. This is the same sinusoidal current here, what we have shown on the left side, and same output on voltage, but there is an offset in the output current, DC offset of appropriate magnitude. That will be self-adjusting. What it is happening because of this offset, now you see this is the charging area and this is the discharging area. And what is happening in this instance, charging area and discharging area, they are getting equalized. So it starts rising from a given point. So through the point it has raised, it comes back to same value at the end of the discharging area, right? So the DC component of current, what is going to flow now, that's finally going to charge the capacitors, and that DC current loop will be like this. It is not going to be percolated in the load because load finally current depends on the voltage over here, and this voltage is not going to change because of the DC current here, neglecting the capacitor voltage ripple. Any question up to this point? Okay. Now, of course, we are not interested to build a multi-level converter because MMC with only one cell per arm over here as shown. So there we replace with multiple modules, and number of modules can be there. So an example we are giving here with 4 modules. So 2V and 2V, the 4V is the total DC bus voltage. So each of the module is having voltage of V. So when I want a voltage of minus 2V here at the output, so we turned on all the modules. So upper arm provides a voltage of 4V and lower arm provides a voltage of 0. So this point gets clamped to negative DC bus and we get minus 2V. Similarly, we get 2V here, just a complementary condition. When both upper arm and lower arm are 2V respectively, then we get output voltage 0. Upper arm is having 3V and lower arm V, then the output voltage is minus V. Similarly, we can get plus V. These are the different combinations. So, of course, there will be option here to get voltage levels 0.5 V, 1.5 V, 2.5 V, etc. Sorry, not 1.5 V, etc. Not 2.5. That's beyond the range. By using this arm inductor as a potential divider, where the sum of upper arm voltage and lower arm voltage will be differing this DC link voltage by an amount of V. Okay. But then if we are doing so and we are getting different levels, we understand that it's likely that these individual cells, in order to build different voltage level, they will not operate at, or they will not be handling some amount of current. That means I mean to say that amount of current handled by them, or amount of power, as a matter of fact, handled by them is going to be different from each other. So whatever charging current coming in from the DC side, what I have shown here by a DC offset here, that current is going to enter in this 4 cells in a different way. So they will get charged or discharged in a different rate. Lower is the switching frequency, more is the deviation between each other. Why, that I cannot discuss now. So what will happen? Even if the charging current is coming, these capacitor voltages will start differing from each other. So that demands something called cell level control. It basically monitors the cell voltage as feedback, takes it as feedback, and then cell voltage reference is there with that PI controller. Depending on arm current direction, it develops a signal which gets added with the modulating signal of the corresponding cell, and that finally makes the modulating signal for the cell. You may interestingly ask here that in such case, the total modulating signal is going to be deferred from the original modulating signal. But then I am adding here, it will not change the final output voltage. Why? Because means amount of deviation from each other. If in one side it is positive, other side it has to be negative. So as a whole, whatever modulating signal with this, we are adding this signal from a PI controller. If we are adding something in one given cell, we have to subtract similar amount of reference from other cell. So as a whole, in an arm, the total voltage reference will not change. Okay. So this is a distributed control cell level. Also centralized control is possible. Which cell will be conducting at which instance, that can be determined by its voltage, extent of discharge or charge occurred in the cell. There can be sorting algorithm. There can be a central processor that can take the voltage from all the cells, and it can run sorting algorithm inside to determine that for a given voltage level, which cell has to be operative. But again, there is another fact. As I said, the AC component of current that keeps on distributed between AC component of current, as I said, those are 120-degree phase shifted. So whatever current coming in here in these 3 upper arms, those are also 120-degree phase shifted. So it will be circulating in between the arms. It will not come to this side. It will not come to this side. Okay. Similarly for the lower arms also, this will be circulating here, and this is called circulating current. But this circulating current of AC component, that's unavoidable. But there is also circulating current. As we see that there is a phase shift in the voltage. So the voltage capacitor voltage ripple in upper and lower arm in these 3 cells, in these 3 phases, those are phase shifted. So this leg voltage, DC voltage at the leg, if we consider that this is a flexible coupling or here some resistance is there or inductance is there, in such case I can say this total DC voltage is V upper arm plus V lower arm. Those will have ripple, and those ripples are phase shifted. Those will cause a circulating current, and that will add, and that will increase the final magnitude of the current handled by the all the components, inductor, capacitor, devices. So peak current for all the components will be increased. So for which the circulating current control is there. But again, it is no rocket science. It again comes from the very basic. Observe that in this basic diagram, what we have drawn here, a delta V amount of difference was coming over here by adding a component here. Now suppose if I add another component, here delta V was added, subtracted here and added here. Now small delta V, if I add in both upper arm and lower arm, that basically reaches the KVL here that finally determine some current. But by adding this delta V components in both upper and lower arm, what happens actually, this output voltage remains unchanged. At the same time, it can ensure that even after having capacitor voltage ripple, the total voltage of upper arm and lower arm remains close to 2V. So this circulating current, because of the deviation of the voltage in the capacitor or the capacitor voltage ripple, that gets minimized, that we call it circulating current control. Okay. So this is the source of circulating current. You see in an arm, always as a whole, the upper arm capacitor and lower arm capacitor together, the total leg is always discharging, whether it is positive cycle or negative cycle. And that discharge is happening, that is having a second harmonic ripple. And those second harmonic ripples are also phase shifted by 120 degrees from the phases between each other. And that causes the circulating current. And by adding a suitable voltage, we nullify it. So that's the block diagram shown here. So we take the upper and lower arm current. If we add them up together, it cancels out the AC current as they go into opposite direction. So if we add the upper and lower arm current, AC component of the current in the arm, that gets cancelled out, and then we multiply by 0.5, what we get DC component of current. And that current reference we want to make as constant as possible, as ripple free as possible. That's why this reference DC component of current is given from here, and that finally generates a signal. So that is finally a voltage which is added to both modulating signal for the upper and lower. As I said here in this diagram, as I have drawn, this small delta V is added both upper and lower. So that's what it's done here. So both upper and lower arm, the signal is added. So that's how the modified modulating signal is generated. Of course, this modulating signal, the arms should be capable of generating this modulating signal. That means when the ripple is there and the capacitor voltage dips to minimum, sum or the arm voltage dips to its minimum, or sum of all cell voltage dips to minimum, then also this modified modulating signal that the arm should be capable of producing. Okay, so that's the essence of circulating current control. And this already I have discussed the impact of phase shifted modulation. So that's it from my side for now. So if you have any question, you can ask further. So yes, with this, I would like to thank for your patient hearing.
Thank you so much for being a part of this STC, sir, and for this wonderful session.
Thank you. I wish to open myself for questionnaire.
Participants, if anyone having any doubt.
Yeah, Mr. Ahis has raised his hand. Yes.
Yes, sir. Sir, can you please share the paper that you are referring to during the first half of your session, where you have shown about the various structures that you have explained?
Okay, this paper you
Title,
can.
yeah.
Yeah, here it is. You can take a snap.
Yes.
It is developed long back. So, and with the development of the new devices, it is expected that in EV market, slowly things can penetrate, but definitely for sure high power, it is already proven. High power application, multi-level converter and CHP, these are already proven. And medium power also, NPC is very much proven, right?
Okay, sir.
Yeah. Any other question? Okay, I
Hello.
especially
Hello.
thank the organizer for giving me 15 minutes extra. So, all right,
No
yeah.
issues, sir. Thank you so much, sir.
My pleasure.
Thank you, sir, for delivering very beautiful and informative lecture, sir. So nice to meet you, sir. Thank you.
Thanks. So if there is no question, then I'll take your leave.
Yes, sir.
All
Thank
right.
you, sir.
Thank you very much
Thank
to all of you. Bye.
Bye.